With the launch at lunchtime of the James Webb Space Telescope, a $10 billion project has taken 30 years to reach this moment, as well as distant planets which could provide evidence of life beyond Earth. Here's our science correspondent Rebecca Morell.
The James Webb Space Telescope has once again expanded the boundaries of human perception by turning its immense gaze upon one of the most intriguing visitors to our cosmic neighborhood. Recently, it succeeded in capturing the first real high-resolution image of R2 Swan, a comet that has fascinated astronomers and skywatchers alike for decades, but has never before been observed in such clarity. The event was more than a technical triumph. It was a symbolic unveiling of how far human technology and curiosity have carried us into the depths of space. Before we start, hit the like and subscribe buttons for more exclusive news. R2 Swan is not a typical comet. Its highly unusual composition, complex chemical traces, and the peculiar brilliance of its coma and tail have puzzled scientists since it was first detected. Earlier telescopes, ground-based observatories, and even Hubble managed only to capture limited data because of the comet's faintness and its erratic brightness. Webb's extraordinary infrared capabilities, however, pierced through layers of dust and gas to deliver a breathtakingly detailed portrait. For the first time, we could see the intricate structures within the coma, the swirls of molecular gas, and the exact texture of the nucleus itself. These are features that were once only guessed at or rendered in simulations. Now they stand revealed in astonishing clarity, offering a new chapter in the study of comets. The unveiling of R2 Swan by Webb is monumental because comets are time capsules from the birth of the solar system. They carry within them frozen remnants of material that has remained unchanged for billions of years. What Webb has given us is not merely an image of a distant icy traveler, but a direct look into the primordial ingredients that formed planets, moons, and potentially even life itself. By analyzing Webb's spectral data alongside the visual imagery, researchers have begun to map the comet's composition with unprecedented precision. They have detected water vapor in distinct jets, complex organic molecules woven through the coma, and an intricate interplay between frozen volatiles sublimating under the heat of the sun. These discoveries confirm that R2 Swan holds not only a wealth of chemistry, but also a deeper story about how solar systems evolve. The visual impact of Webb's capture is nothing short of stunning. Where once R2 Swan appeared as a faint smudge against the darkness of space, it now blazes forth in layers of radiant detail. The coma, glowing in hues invisible to the human eye but translated into visible light, extends outward like a veil of fire. The tail, stretching millions of kilometers, reveals braided patterns and faint secondary jets, each one a fingerprint of the physical processes unfolding within the comet. The nucleus itself, though tiny in comparison to its luminous shroud, emerges as a rugged, icy relic, scarred by the countless journeys it has made across interplanetary space. This kind of resolution was once unimaginable, but Webb's sensitivity has transformed a dim wanderer into a detailed object of study. The implications for planetary science are profound. By capturing R2 Swan in such detail, Webb has provided a model for future comet observations. Each new comet that enters the solar system can now be dissected with this same method, enabling researchers to build a comparative archive. Such a collection would illuminate differences in comet origins, reveal the various pathways comets take in their long orbits, and shed light on how they transport material across planetary systems. Already, some astronomers are suggesting that Webb's view of R2 Swan could be used as a benchmark against which to measure other comets. This single event may well mark the beginning of a new era in cometary studies, one defined by a standard of precision never before achieved. Beyond the technical and scientific outcomes, the cultural and philosophical implications are equally profound. Humanity has always looked to comets as omens, mysteries, or cosmic symbols. They appear suddenly, blaze for weeks or months, and vanish again into the abyss, reminding us of both the fragility and the vastness of existence. The James Webb Space Telescope's image of R2 Swan is more than a scientific record. It is a modern myth, a new way of connecting the human imagination with the vast workings of the cosmos. The ancient fear of comets as harbingers of doom is replaced now by awe, curiosity, and wonder, fueled by the fact that we can see them as they truly are. What makes Webb's capture of R2 Swan so remarkable is also the timing. Humanity is on the brink of expanding deeper into the solar system, with missions planned for the Moon, Mars, and beyond. Understanding comets is not merely academic. These icy wanderers may one day serve as waypoints, sources of water, or even fuel depots for interplanetary travel. By learning their structure, composition, and behavior, we prepare for a future where encounters with comets are not just distant observations, but practical considerations for exploration. Webb's image therefore speaks both to our past and our future, revealing the primordial building blocks of our solar system while pointing toward the era of human expansion into space. The scientific community has been quick to dive into the wealth of information encoded in the Webb image. Detailed spectrographs show a variety of volatiles outgassing from R2 Swan, including carbon monoxide, methane, and ethane, each a piece of the chemical puzzle that hints at the environment in which the comet formed. The presence of complex organics is particularly tantalizing, as it strengthens the hypothesis that comets may have delivered prebiotic molecules to early Earth. If that is true, then comets like R2 Swan were not just visitors, they were couriers of the very chemistry that led to life. Webb's observation is not proof of this theory, but it gives it sharper definition, making the case more compelling than ever. For astronomers, the excitement also lies in Webb's ability to track the dynamic changes in R2 Swan over time. Comets are not static objects. They evolve as they approach the sun. Jets flare, dust tails shift, and the balance of volatiles changes with every degree of solar heating. With Webb's sensitivity, these changes can be charted in exquisite detail. This allows scientists to model not just the structure of a comet, but its behavior in real time. Watching R2 Swan transform under the heat of the sun gives us a living laboratory for processes that also shape the early solar system. Every flicker of activity in the comet's jets is a clue to the delicate balance of ice, rock, and sunlight that governs cometary life. The visual data also serves as a powerful educational and inspirational tool. For the public, seeing R2 Swan through Webb's eyes is a reminder of what humanity can achieve when it reaches outward with curiosity. Students, artists, and everyday skywatchers can now look upon a comet not as an abstract dot, but as a detailed, vibrant world in miniature. The awe inspired by such imagery fuels interest in science, draws more minds into astronomy, and strengthens the shared sense that we are participants in a cosmic story much larger than ourselves. Webb's image is not just for the scientific journals. It belongs equally to the human imagination. The symbolism of the name R2 Swan also cannot be ignored. The comet, passing through the constellation Cygnus, the Swan, seems almost destined to be revealed in such majestic detail by Webb. Cygnus has long been associated with myth, beauty, and transcendence, and now, within that celestial backdrop, a comet has been unmasked in a way that merges myth with science. This poetic resonance deepens the impact of Webb's achievement, reminding us that science and storytelling are not separate endeavors, but two lenses through which we interpret the universe. In a broader sense, Webb's success with R2 Swan also demonstrates the telescope's versatility. Designed primarily to study the earliest galaxies, the birth of stars, and the atmospheres of exoplanets, Webb has shown that its abilities extend just as powerfully to objects within our own solar system. This versatility makes the telescope a universal tool for astronomy, one capable of linking the distant and the near, the cosmic and the local. It is a reminder that the same forces shaping a galaxy billions of light years away are also at work in the icy heart of a comet that sweeps through our skies. The image of R2 Swan captured by Webb is not a conclusion, but a beginning. It opens pathways for new research, new collaborations, and new questions. How many comets share R2 Swan's unusual composition? What can these icy wanderers teach us about the migration of material across the early solar system? Could studying their chemistry refine our understanding of how habitable worlds emerge? These are questions that will occupy scientists for years to come, fueled by the clarity of one image and the possibilities it unveils. As humanity reflects on this achievement, there is also a quiet recognition of what it represents about our species. The act of sending a telescope 1,000,000 miles into space to capture the delicate image of a comet speaks to a unique combination of curiosity, ingenuity, and perseverance. It shows that even in an age of countless distractions, we still invest in peering outward, still dedicate ourselves to expanding knowledge, still reach for the stars in both literal and figurative senses. Webb's portrait of R2 Swan is not just a scientific milestone, it is a mirror held up to humanity's enduring spirit of exploration. The journey of R2 Swan across the heavens will continue, and it will eventually vanish once again into the cold darkness of interstellar space. But Webb has ensured that its passage will not be forgotten. For the first time, we have not just a fleeting glimpse, but a lasting record, a detailed testament to its existence and its significance. The comet may depart, but its story remains imprinted in the annals of science, etched into the collective memory of humankind through the lens of the most powerful telescope ever built. The capture of R2 Swan by the James Webb Space Telescope does not simply sit as an isolated accomplishment in astronomy. It reverberates outward, touching fields as varied as astrochemistry, planetary science, and even philosophy. The story of this image is a tapestry woven from countless strands of inquiry, and when examined deeply, each strand reveals new dimensions of meaning. To expand the discussion, one must step further into the many implications of what Webb has done and what it represents for humanity's understanding of the universe. The ability to study a comet like R2 Swan in such detail represents a monumental expansion in the reach of spectroscopy. For decades, astronomers have sought not just to observe light, but to dissect it, to break down every wavelength into a story of molecules, atoms, and chemical processes. When Webb pointed its instruments toward this icy traveler, it collected not just a picture, but a vast library of spectral fingerprints. Each emission line, each absorption band, carried the mark of a specific molecule or atomic species. From water vapor to carbon monoxide, from methane to more complex organics, Webb's detectors revealed a chemical orchestra. What makes this significant is not just the list of molecules, but the way they interact and vary across different regions of the comet. Mapping the distribution of these chemicals in 3 dimensions allows scientists to reconstruct the internal architecture of the nucleus itself. No previous telescope has ever provided this level of insight into a cometary body. This level of spectral detail is invaluable because comets are heterogeneous objects. They are not uniform ice balls, but patchworks of materials with different volatiles embedded in different layers. Some parts may release carbon dioxide at lower temperatures, while others might hold on to methane until closer approaches to the sun. Webb's image of R2 Swan paired with its spectral analysis effectively peels away the layers of the comet like pages of an ancient book. Each layer speaks of a different time in the early solar system, a different environment in which dust, ice, and organics condensed and coalesced. Thus, the telescope is not merely observing a transient phenomenon in the present, it is conducting a forensic investigation into events that took place over 4.5 billion years ago. Another crucial dimension is dynamics. Comets like R2 Swan are not inert. They are active engines of change. The interplay between sublimating ices, escaping gas, and the gravitational tug of the sun transforms them from moment to moment. Webb's high temporal resolution allows astronomers to watch these changes as they happen. By monitoring the flickering activity in the jets and the shifting structures in the tail, scientists gain real-time data on how volatiles behave under solar heating. The patterns Webb has revealed, braided filaments in the tail, curling plumes erupting from vents, are not just visually spectacular, they are physical clues to processes that drive cometary evolution. These processes, in turn, mirror the same mechanisms that once redistributed material throughout the infant solar system, carrying water and organics from beyond the frost line inward toward young rocky worlds. The discovery that R2 Swan harbors complex organics is especially tantalizing. Life as we know it is built on carbon, and carbon chemistry thrives in complexity. When Webb identified molecular structures that go beyond simple volatiles, it pointed toward a cosmic chemistry laboratory operating far from Earth. The implications ripple outward. If such molecules are common in comets, then every solar system may have reservoirs of organic complexity drifting in its outer regions. The delivery of such molecules to young planets through cometary bombardments could be a universal phenomenon, a step in the chain that makes biology possible throughout the galaxy. The image of R2 Swan is, therefore, not just a portrait of an icy visitor, but potentially a snapshot of a mechanism that seeds life across the cosmos. To grasp the scale of this achievement, one must reflect on the technical marvel of Webb itself. Positioned at the Earth-Sun L2 point, shielded from stray heat and light by its massive sun shield, the telescope exists in a realm of silence and precision. Its gold-coated mirrors gather photons that have traveled millions or even billions of kilometers, funneling them into instruments so sensitive that they can detect the faint whisper of molecules around a comet. This engineering triumph is what allowed R2 Swan to be revealed in such fidelity. Without Webb's cryogenic stability and extraordinary resolution in the infrared, the comet would remain a blur, its secrets locked away. The success demonstrates not only the power of human invention, but the foresight of generations of engineers, scientists, and visionaries who imagined a tool capable of such feats. Another fascinating dimension is the way Webb's image reshapes the narrative of comets in culture. For centuries, comets were regarded as unpredictable, chaotic intrusions into the order of the heavens. They appeared suddenly, seemed to defy the fixed motions of the planets, and then disappeared into darkness. The fear and superstition surrounding them were products of their mystery. With Webb, that mystery is not erased but transformed. Seeing R2 Swan in such exquisite clarity does not diminish its wonder. It amplifies it. Now the comet is no longer a faceless omen but a tangible, textured world, with features and behaviors we can study and even admire. This shift marks a profound cultural evolution, where human fear of the unknown is replaced by reverence for knowledge and discovery. There is also the question of scale. Comets are small compared to planets, often only a few kilometers across. Yet their influence has been outsized in shaping planetary surfaces, atmospheres, and possibly biochemistry. Webb's image of R2 Swan underscores this paradox, a tiny, icy body that glows with cosmic importance. The nucleus of R2 Swan might be smaller than a large metropolitan area, yet the tail stretches across millions of kilometers of space. This juxtaposition highlights the strange duality of comets: minuscule origins, colossal impact. By giving us a direct look at this duality, Webb invites reflection on the disproportionate roles that small bodies can play in the cosmic theater. The timing of Webb's observation also opens new possibilities for predictive science. By monitoring R2 Swan and similar comets over time, astronomers can refine models that forecast how comets will behave during future passages near the Sun. These models are vital not only for scientific curiosity but for practical concerns. Comets can and do intersect with planetary orbits, including Earth's. Understanding their structure, fragility, and activity patterns could one day prove essential in planetary defense strategies. Webb's data provides the foundation for such models, ensuring that humanity is better prepared to anticipate and respond to the motions of these cosmic wanderers. R2 Swan itself is an object of intrigue because of its trajectory and origin. Its orbit suggests it hails from the distant Oort cloud, a vast hypothetical shell of icy bodies that surrounds the solar system. These objects are stirred from their slumber by gravitational nudges from passing stars or galactic tides, sent hurtling inward where they briefly flare as comets before retreating again. Webb's image of R2 Swan thus doubles as an indirect window into the Oort cloud, a region too distant to be observed directly. Every detail in the comet's structure is a clue to the environment at the edge of the solar system, where stars intermingle and icy bodies have drifted untouched since the dawn of planetary formation. The revelation of detailed organics also sparks questions about diversity among comets. Are all Oort cloud comets rich in such molecules, or is R2 Swan unique? Do comets from the Kuiper belt closer in exhibit different signatures? Webb's ability to capture and catalog multiple comets in the years to come will provide the answers. By comparing R2 Swan to future observations, astronomers can map the chemical geography of the solar system's outer reaches. This will clarify whether organic richness is widespread or concentrated in certain populations, thereby informing theories of solar system development. It is worth considering the visual artistry of Webb's image as well. The glowing arcs, shimmering jets, and radiant veil of R2 Swan are not only scientific data points but cosmic art. The translation of infrared wavelengths into visible colors produces a portrait that blends science and aesthetics seamlessly. To the human eye, the comet appears almost painterly, a living canvas of light and motion. This aesthetic quality is not incidental. It is part of what makes such discoveries resonate with a broad audience. Science communicates through numbers and equations. but it also communicates through images that stir emotion. The portrait of R2 Swan is one of those images, destined to hang in the gallery of humanity's most iconic glimpses of the cosmos. One cannot ignore the broader context of Webb's mission. While designed to study galaxies at the edge of time, its ability to turn its instruments toward objects within our own solar system underscores a unity of cosmic investigation. Whether looking back billions of years to the first galaxies or peering at a comet today, Webb reveals connections. The same physics governs both realms. The processes that shape the icy nucleus of R2 Swan are kin to those that built the cores of galaxies. In studying the small and the local, we gain insight into the vast and the universal. The comet thus becomes a bridge between scales, linking human experience to the grand architecture of the cosmos. The philosophical implications are just as deep. In gazing upon R2 Swan with such clarity, we confront once again the question of our place in the universe. This tiny comet, hurtling through the void, carries within it the raw material for planets and life. In a sense, it is kin to us. The atoms that compose it are the same atoms that compose Earth, and by extension, ourselves. Webb's image makes visible a literal connection between humanity and the cosmos, between flesh and ice, biology and chemistry. Such reflections remind us that science is not only about measurement and analysis, but about meaning, about weaving our existence into the larger cosmic story. This achievement also sets the stage for interdisciplinary exploration. Astrobiologists, geologists, chemists, and astronomers can all draw from Webb's data to pursue their own lines of inquiry. The comet becomes a crossroads where disciplines intersect. Geologists may model its surface processes, chemists may analyze its organics, astrobiologists may speculate about its role in delivering precursors to life, and astronomers may refine its orbital history. This convergence fosters collaboration, creating a richer and more nuanced understanding than any single field could achieve alone. From an educational standpoint, the capture of R2 Swan offers a case study in the scientific method at its most inspiring. Here is an object once shrouded in mystery, now rendered clear by observation and analysis. Students can follow the arc from detection to imaging to interpretation, seeing firsthand how questions lead to hypotheses, how hypotheses are tested, and how knowledge expands. The comet becomes a classroom in the sky, its every detail a lesson in physics, chemistry, and cosmic history. The first real image of R2 Swan taken by the James Webb Space Telescope opens another dimension of reflection when one considers how it links our own solar system to planetary systems beyond. Comets are not confined to the sun's domain. They exist in countless other star systems as well, orbiting in icy belts and reservoirs far from their central stars. These cometary analogs, sometimes inferred through circumstellar dust or through unusual transits of exoplanets, have remained abstract to us. Webb's image of R2 Swan allows us to construct a detailed model of how comets look and behave in their active states, and this model can be projected outward, helping to interpret distant exocomet phenomena. The detailed structure of jets, tails, and comae that Webb has unveiled becomes a template by which astronomers can decode faint signals from comets orbiting other suns. This comparative approach not only enriches our understanding of our solar system, but gives us the keys to unlock the dynamics of alien ones. The chemical revelations within R2 Swan also provide a direct connection to the field of exoplanetary science. The detection of volatile species like methane and ethane, coupled with organic chains, mirrors some of the atmospheric chemistry astronomers hope to detect in exoplanets orbiting in habitable zones. By seeing these molecules erupt from a cometary body within our reach, scientists can better understand the kinds of signals Webb might detect when it studies exoplanet atmospheres. The comet becomes both a laboratory and a benchmark, allowing researchers to refine their interpretation techniques so they are prepared when Webb peers at distant Earth-like planets. In this sense, R2 Swan is not only telling us about itself, but preparing us for discoveries yet to come. From a geological standpoint, the rugged nucleus revealed by Webb offers an entirely new perspective on cometary surfaces. High-resolution imaging indicates fractures, pits, and vents that hint at cycles of heating and cooling stretching across multiple passes around the Sun. These features suggest that comets are not static, but evolve dynamically over their lifetimes. For geologists, This means comets can be read like planetary surfaces, with their landscapes recording histories of activity and stress. The ice cliffs, shadowed depressions, and vent scars visible in Webb's image tell a story of internal pressure, sublimation, and collapse, each feature marking an episode in the comet's biography. Studying this geological record helps refine models of how small bodies age and disintegrate, a process that has implications for everything from planetary defense to the formation of asteroid families. The presence of multiple jets, braided tails, and dynamic outgassing raises questions about the internal structure of R2 Swan. Rather than being a homogeneous ball of ice and dust, Webb's observations support the model of a fractured and porous body, with pockets of volatiles trapped beneath crusts of hardened material. When sunlight reaches these pockets, pressure builds until the surface ruptures, producing the dramatic jets observed. Such behavior suggests that comets like R2 Swan are fragile, loosely bound conglomerates rather than solid monoliths. This fragility plays a critical role in determining how comets evolve over time and how they interact with planets they encounter. It also informs mission planning, since any spacecraft sent to sample or land on a comet must contend with these unpredictable eruptions and structural weaknesses. The artistic and cultural significance of Webb's image cannot be overstated. In many ways, R2 Swan represents a turning point in how humanity visualizes comets. For centuries, artists could only paint what they saw with the naked eye, faint glowing arcs across the sky. Even with telescopes, comets remained ghostly smudges. Now, with Webb's image, we see a level of detail that transcends mere observation. The comet's veil of gas and dust is rendered in a palette of colors derived from infrared wavelengths, a translation of the invisible into the visible. This transformation is not just scientific but aesthetic, as it provides humanity with a new visual language for understanding cosmic phenomena. Future generations of artists, filmmakers, and storytellers will draw from these images, weaving them into cultural narratives that extend beyond science into art and imagination. The image also prompts reconsideration of the role comets play in shaping planetary environments. Beyond their role as chemical couriers, comets have historically altered planetary surfaces through impacts. Webb's revelations about R2 Swan's volatile richness add new weight to the idea that cometary impacts could have repeatedly transformed Earth's surface and atmosphere during its early history. By studying how volatiles are stored and released in comets, we can infer how much water and organics might have been delivered during these bombardments. The question of Earth's oceans, whether they originated from comets, asteroids, or outgassing from the mantle, remains open. Webb's contributions through R2 Swan tip the scale toward a hybrid model, in which comets play a more significant role than previously thought. This changes how we imagine the early Earth, not as a dry rock gradually moistened, but as a world profoundly shaped by the chemistry of visiting icy bodies. The comet also provides an extraordinary opportunity for education and outreach on the mechanics of infrared astronomy itself. Webb's instruments detect light invisible to human eyes, translating heat signatures into visual maps of structure and chemistry. This requires careful calibration and interpretation, turning what is essentially data into imagery that communicates across scientific and public audiences. R2 Swan's image demonstrates this process beautifully. What was once a hidden world of infrared emissions is now displayed as a glowing, intricate object. Students learning about spectroscopy and astrophysics can see in real time how instruments convert raw signals into vivid understanding. This transparency and methodology makes science tangible, empowering the next generation to engage with it not as mystery but as an achievable pursuit. There is another layer to the significance of Webb's capture, and it lies in its demonstration of international collaboration. The telescope itself is a product of partnerships between NASA, ESA, and CSA, built by thousands of individuals across continents. R2 Swan's image, therefore, is not just a triumph of one nation, but of humanity as a whole. It symbolizes what can be achieved when countries and cultures pool resources, intellect, and vision toward a shared goal. The comet becomes a shared treasure, its image a universal artifact of human cooperation. In a world often divided, the ability to unite under the banner of discovery provides a reminder of our collective potential. From a technical standpoint, Webb's ability to capture the faint halo of R2 Swan demonstrates its unparalleled sensitivity to diffuse objects. Whereas earlier telescopes struggled with the contrast between faint cometary gas and the surrounding darkness, Webb's detectors excel at isolating subtle emissions. This capability will be invaluable not only for comets, but also for studying faint nebulae, planetary atmospheres, and diffuse interstellar clouds. R2 Swan thus serves as a proof of concept, showing how Webb can push boundaries in detecting and analyzing the faintest whispers of light in the cosmos. Webb's image of R2 Swan invites contemplation of time itself. The comet is a traveler on a vast orbit, its path shaped by gravitational encounters, its surface reshaped by each pass near the Sun. Webb's capture is but one moment in this long journey, a snapshot of activity that will soon fade as the comet retreats to the darkness. Yet this single image freezes a cosmic moment for eternity. It allows us to hold in our hands, figuratively, a fragment of time that would otherwise be lost. This act of preservation is itself profound, for it demonstrates humanity's ability not only to observe but to memorialize the fleeting phenomena of the cosmos. Comets pass, stars evolve, galaxies drift, yet through instruments like Webb, their stories are captured and shared across generations. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on James Webb capturing the first real R2 Swan image? We want to hear from you. Thank you for watching, and see you next time.